today. Let's see. Hello, everybody. Welcome to the CU Boulder Topology Seminar. Today, our speaker is Professor Vasileios Maroulas from the University of Tennessee, and he will speak about random persistence diagram generator and an application to materials.
All right. So thank you very much, Marcus, for inviting me today. Give this talk in the topology seminar. Let me start with this, that I'm a statistician by training. So the talk is going to be a little bit different. I hope I don't disappoint you. But on the other hand, it's more or less kind of like throwing a bridge at you, kind of like, you know, how you could view things in a different way, and perhaps you could help collaborate in the future if you are interested in that stuff. So I have a different viewpoint. Again, some of the things that will be very familiar to you, some other things that will be a little bit different from what perhaps you might be you have seen before. Okay, so first of all, let me say that the work that I'm going to say today is basically based on the very first paper, and some of these actors there are my collaborators, Papa Markov from Manchester and Nazarene from University of Hawaii, and my material science friends, Nat Gong and Orlando Rios. These are the main collaborators in this project. And actually, this project actually has two sides of the same coin. It's not like only statistical and topologically interesting, but at the same time, provided a solution to material science for something that I will speak today. And also we have like, you know, a more material science, if you like, publication that talks about this with various other people's that they did experiments, because all the data here are true experimental data in the lab. Okay, so and also let me acknowledge also funding by various agencies that you see here. Thankfully, they trust their money to us, and I would like to thank them for that. Okay, so I'll start this talk by introducing the problem in a bigger umbrella, like what it's about. And then I'm going to delve into at least how I view this problem. And the idea is now between how to make statistics and topological data analysis together to get a product out. That product led to something that it is what I call is a random persistence diagram generator. The same, you could think of that as an analog. You have a number generator. Okay, so I developed a random persistence diagram generator. And that was very useful to basically apply to this material science data and precisely the austentized stainless steels. Okay, and why you need a generator for that stuff? Because the experiments are very expensive. So they can have only one specimen. So if you really want to do a safe data analysis for this data, you just have to somehow generate something, a persistence diagram now, in this application. You need to generate something that it will basically abide by the physical and the chemical properties of the true experiment. Okay? So after I say all that, I will conclude, and I know I'm between, you know, the end of the day for you, and you know, so I'll try to be brief, and I hope you enjoy. Okay, so high strength steels. It's a very important and fundamental for the economy, you know, material. Okay, so any advancement that you do for it, then it's very important for our industry and for our life in general. So on the left hand side, you see like you know, an E-cup. Okay, is so high strength steels are used for that, and this is a vehicle, and everything that it is colored is basically where high strength steels are being used. So you could see like pretty much the entire framework of the vehicle is based on these materials. Okay, so why do I care about specifically about the austenitic stains? So first of all, are commonly available. 60% of these steels are of austenitic steel style. So if you are interested about its consistency, it is 18% chromium, 8% nickel, and basically the rest is titanium, nitrogen, and other elements. Okay, so why it is a good material? Great plasticity, toughness, weldability, and corrosion resistance. Also, it has superior impact, blast, and seismic performance. And if you don't care about that, at least they look good. Okay. So, for example, you see the cloud gate in Chicago there, which is a type 316L austenitic stainless steel. Okay, and it is exposed in Chicago to this ice and salt all the time, but still looks pretty good. Okay, we all go there and take pictures, and we mirror ourselves. So, what's happening? So, what I'm going to be interested, what kind of data based on these materials? Okay, so our materials friends do this electron backscatter diffraction experiment. So what do they look there? There they look at the crystals in a material. Okay, so the idea is basically when the metal starts solidifying, then millions of crystals are created. The longer it takes to solidify, then the longer these crystals will be more prominent. Okay, and it's gray now. Within the crystal is a distinct crystal with its own orientation. Okay, and how they are sitting on top of each other, perhaps it actually may lead to fracture easier or not so easy. Okay, so material scientists do look at these properties. Okay, and how do you do that with the electron backscatter diffraction? So I'm going to be very hand wavy here. So the experiment is you have the specimen in an angle, the electron beam hits it, and then reflects back on a phosphorus screening camera, like the backscattered electrons, and then you capture images of that. Okay, you capture images of the grains. So how these look like? Exactly as you can see on the ABCDE. These are the structures I'm going to study today. Okay, these are coming from real annealed austenitic stainless steels in various temperatures from 700 Celsius all the way to 950 Celsius. Okay, so if you look at A, B, C, D, and E, one may say, what one may say? What do you think? Would this material behave in a similar way, in a different way, in various temperatures? What does your gut feeling tell you about? And if it doesn't tell you anything, that's okay too, right? I mean, that's why we do analysis.
What are the graphs? Like, what are the x-axes? It's a little small to read.
Oh, I'm sorry. Okay, that was too big. Just look at A, B, C, D, and E. Okay, so the colors here represent, sorry, the guys here, these are crystals of the same material, okay, as it has been captured in the experiment. And then the different colors represent some parameter, let me put it that way, okay? So, and this is the parameter we're going to study. Don't worry about the right-hand side, the columns, the histograms, yet just look at these pictures. And if you look at these images, can you say something about that? Pattern-wise, don't worry about what is X, what is Y, or what the colors might be. So, for example, I may notice that B, C, D, okay, and perhaps A, they're very grainy. They have very small little bit, here and there. Okay, so it's kind of like you are on the East Coast where the states are very small. Okay, But E, somehow like they start enlarge the grains. Okay, so the A, obviously you are hit by a lot of sparsity because you have a lot of empty spots, okay, that they haven't been formed. So, but still kind of, the very bottom part has kind of like larger grains, but the very top is really grain, very, very tiny grains. So, and basically, let me go back to normal size. So the idea basically is, can I differentiate that? Okay, so if I'm thrown these various 5 images, it's only 5 images. Can I basically differentiate the behavior in what sense? The B, C, and D, ideally, I would like to group them together. The A is a little bit different, but it has to do with the sparsity, still grainy, but certainly E is not grainy at all. Is not like, has larger grains. So the idea is, can I differentiate these various behavior? Okay, and what the material scientists actually are very interested is the breaking point here, that they should see difference in behavior of the material is at 900 Celsius. So the 950 should definitely behave differently than the rest. So what our friends in material sciences do, they consider like a parameter, they call it Schmidt factor, okay, which basically would evaluate the ease of dislocation movement within a grain, okay, and this is related to the plasticity and stress properties, and which is the various different colors on A through E, and they do histograms. You look at the histograms, the red histograms there, and the idea is they run a test how different the histogram A may be from histogram B, from histogram C, from histogram E. Okay, so in statistics, don't know if you've heard of it, this is the Kolmogorov-Smirnov test that they basically want me to do. Okay, this is a very typical test that one will test distributions of things, how different they might be, significantly different or not. Okay, and this is what they have done. Okay, so the idea here is, though, for me, is I'm gonna still stick to the Schmidt factors because that's what they do. It's a very easy, it's a number that they are interested. Let me put it that way. And use some statistics and topology to basically try to understand the data and classify. Okay, classify them mean, as I said, whatever is A, whatever is B, B, C, D, and E. And as a matter of fact, what I'm gonna do is A through D should be the same, but the material scientists know that E should be different. Okay, so hopefully we'll reveal that. So why topology? Topology because we're talking about shape of data, but data comes with uncertainty and noise. So you need the statistics, and that's why I'm merging them too. Okay, and these are various studies that and various different applications that I have developed algorithms between topological data analysis, statistics, and machine learning. Okay. So, okay, I know you are experts, but for the sake of completeness of this talk, let me just say the idea here, we're going to consider a simplicial complex. In my viewpoint, I view it as a generalized graph that basically has richer relationships than just nodal information. And the 3 bullets next are in a hand wave the definition of a simplicial complex. Okay, not gonna say more in here. So if you try to do this with data, so perhaps you have here the Vietoris-Rips filtration. If not, I'm gonna go through it. So on the left-hand side is the point cloud data, the data. And then in the middle is gonna be my scratch paper, and on the right-hand side is gonna be another scratch paper. that what I'm going to do. Okay, so I start with circles of radius epsilon around each datum. The algorithm asks the question: do the circles intersect? Yes or no? The answer here is no. You do absolutely nothing in the middle, and then on the right-hand side, you're gonna have bars as long as the epsilon, the radius you chose to start with. Okay. You increase it, the radius, so you're gonna get increasing sequence. You're gonna get an increasing sequence of radii of epsilons. So I increase it to 71%. So the algorithm asks the same questions: do circles intersect? Here is yes. So which ones over those three on the top? So you go and you put edges, and that means beyond 0.71, you are going to treat these three nodes as one. So two of the bars on the right hand side, they're going to get killed. Okay. And here 0.9, you can see that beyond. Okay. Beyond 0.71, then these two bars here, this one and this one, they just stopped. Okay, so you move on. You increase the radius now 1. Okay, so lots of things happening here. So first of all, a lot of circles intersected. Okay, so from now on, I'm gonna have the house here that I'm gonna be treating as one thing. And then these two together, all right? But also at the same time, these three circles, for example, intersected at the same time simultaneously. So it's a three-way communication. So you go and you fill in that this thing here with a triangle, okay? With that face, okay. But also you have an empty spot, a hole right here. So with a different color, a different label, if you want to speak machine learning, you're going to be basically tracking the evolution of this hole. Okay, so you do that, you move on. So here you see beyond 1, you could see that you have 2 bars that they represent this guy here and this guy right here. Okay, and the red is tracking that hole. Okay, so you go one up, 1.25. All right, so now you have a house with a garage. Okay, so everything is so the black bars, you're gonna have only 1 from now on, but also you got another hole right here, so you'll be start tracking it with a second red label. Okay, and you keep increasing. Now this hole got filled in, this one remains here. Okay, so now all the circles, all the data points, the original data points kind of communicate with each other. So it is safe to end the algorithm now because it's not going to give you anything anymore. Okay. All right. So this is the barcode. So basically what happens is I started with the original data on the right hand side, and then I evolved this with the method we just described. I got this barcode, but now if you use different coordinates, birth and death, you get something that is called a persistence diagram. Okay, so and the black dots represent the H0 homology basically, and then H1 is the triangles. Okay, so the holes. Okay, so the idea now is, can I use this as a summary of the shape of the data to basically capture the behavior, the shape behavior of the data? But we're not done yet, because if you look at this note that you have there, okay, this is a type of a Celtic note. If you have perfect data, the persistence diagram looks 1, 2, 3, 4. These 1 and 2, they are kind of coincide on a persistence diagram on top of each other. And the same as 3 and 4, which is for the smaller loops. But data never comes in the form of perfection. Data has uncertainty, data has noise. And for example, if I am lucky, it might come something like that, which I can eyeball it. But this affects the persistence diagram, and the persistence diagram is going to look like the way you see it here. As you can see, the 1 and 2 have been differentiated, the 3 and 4 have been differentiated, and then you have the blue region down there, which I have clustered it as 5, which basically is the driving noise, the underlying noise in the process. So the idea is here I have to take this summary, this topological summary for my data, but also engage it with statistics to try to understand the noise. By the way, here on the persistence diagram, I rotate it because it is birth and persistence, meaning death minus birth. Okay, that's why there's no diagonal anymore. I prefer to work with the quadrant rather than the upper wedge. No particular, just makes it easier. Okay, now statistics and persistence diagrams. So at the beginning, when people started looking at that stuff together, how they merge statistics and persistence diagrams, they were given a lot of summary statistics, the center, the variance, in Freset sense, the Freset variance and stuff like that. Okay, so there are really good studies about these things. People would consider a metric for the persistence diagram space, and then do some probability statistics with it. Other folks went more of a stochastic process, if you like, more of a birth-death type of evolution with that. Also we had some confidence bounds by the Carnegie Mellon at that time group of Wasserman. But the idea is when you try statistically to summarize something, that summary needs to carry the entire information. So for example, if I give you like 10 numbers and then I get the average, the mean might be the mean is a sufficient statistic. In a sense, it carries the information about this data somehow. The persistence diagram, unfortunately, is not a sufficient statistic unless you look it up on under the scope of tropical geometry. I'm not gonna go there, but so in 2019 there was this like really interesting paper on how you can use sufficient statistics in persistent homology using tropical geometry. And also they were talking about consistency. I think I talked in the morning with you about consistency. So so I found this for you. So the topological consistency via kernel methods by Bobrovsky and collaborators. Okay, so this is all fantastic, but we are talking about how to summarize persistence diagrams. But to me, philosophically, is a little bit interesting. In what sense? I have my data, I topologically summarize them, and then I'm going to summarize what I summarized. So a lot of information may be missing in between. So the idea is, can I consider a probability distribution for these persistence diagrams? Because then if I know the probability distribution, then I know pretty much a lot of things about the uncertainty of the persistence diagrams and how they behave. So I started looking more onto the probabilistic settings of PDs, of persistence diagrams. And to me, that very first paper is kind of an influential paper because they kind of gave a structure how you could consider probability measures on persistence diagrams. And that's by Sayan and Mileko and Hale. Okay, and then personally with my research group, I started like developing non-parametric methods to estimate these persistence diagrams, distributions of persistence diagrams, because it's one thing to have the theoretical setting, but if you wanna write an algorithm about it and draw samples, you really have to have an estimate about this. You have to have a formula. For example, is it Gaussian? It's not Gaussian, but I'm just saying. Okay, And also we went into the Bayesian perspective because experimentalists do carry prior knowledge about their experiments. So we wanted to fuse that prior knowledge into the analysis. And that's why it is a Bayesian. Okay, but today we will be talking about how, let's say I have a distribution, how can I draw samples out of that? And the thing that comes in mind is a Markov chain Monte Carlo. A Markov chain Monte Carlo would basically, you could draw samples out of a distribution. Now, Adler considered an MCMC method using a Gibbs measure for persistence diagrams. Okay, and in a follow-up paper had something similar like that, but it was a non-parametric method for differentiating noise, topologically prominent points from noise. So this 1, 2, 3, 4, 3, 4 that I had earlier from the blue region 5. Okay, so so before going there, let me, in case you are not familiar with Markov chain Monte Carlo. So these are kind of the 5 plus 2 more bullets I will show you that you need to know about this method. Okay, and all the rest is just details, but these are the really big letters about. So MCMC basically you generate samples while you explore the state space. Okay, now this mechanism, this algorithm is basically constructed so that the chain spends more time in the important regions. Okay, so wherever you have modes of distribution, that's where your samples should be drawn from. Okay, the chain is constructed in that way that the samples mimic samples drawn from the underlying distribution. Now, the saddle point is the distribution that I'm drawn out of these MCMC samples, there is not going to be perfect, okay, because there is a normalizing constant there, and that is very hard to evaluate it. Okay, why it is hard to evaluate it? Because it is really high dimensional. So think of it as an integral over a high dimensional space. Okay, so it's extremely hard to do that. So now the most popular method is the Metropolis-Hastings algorithm. Don't know if you ever heard of it, but that's what it is. So what does the Metropolis-Hastings do? Well, it tells you, okay, look, I know this is the target distribution, but it is instead of drawing out of this, I'm going to propose something different. Okay, there are some theoretical bounds there are some theoretical constraints about that, how you do it. So you do that, and then you are going to accept this sample that you just drew by looking at this acceptance probability here. So you could view this ratio right here as basically as a penalty that you pay, if you like, for not drawing samples from the underlying distribution, but yet drawing samples from something different. Okay, that's how you could view this. Okay, so we're going to do this, but for persistence diagrams. Now, the difference is a persistence diagram has an X and Y coordinate, so it is scattered on the space. So if it is scattered on the space, it means that I need to use an underlying point process. So a process that is going to work on 2 dimensions in some sense. Okay, so the simplest point process that you can think of is a Poisson point process. In what sense? I'm going to get, let's say, 5 balls. Think of it as taking 5 balls, grabbing them and throwing them on the floor, and then they just, they just scatter there. Okay, and then I do it again and again and again. Okay, out of this Poissonian point process. Okay, we're going to do a Poisson here, but the persistence diagram have a little bit of they have a tweak to it. In what sense? where the points appear on the persistence diagram, it really depends on the very noise. It depends on how these points, like how when you start growing this ball. Sorry, that was weird. So when you start increasing the radii, so the problem here is the points on how they appear interacting with each other. Okay, so we're gonna consider like an interacting point process, as a matter of fact. So the underlying point pattern for the persistence diagram is going to be given according to equation 1. So the blue equation is how you take them and you throw them on the floor, but the red one takes care of the interaction between them. Okay, the interaction between points. So if you want to do more of a math physics kind of idea, and then you consider a potential, so you can rewrite this equation number 2 according to this, and then your potential is that equation number 2 there. I didn't do anything fancy, but computationally, this is advantageous to use logarithms rather than these guys over there in equation number 1. But that's the potential that one may use. Now, Adler, what he did and his collaborators they did in the work is basically they consider a cluster of points. Okay, so they consider a cluster of points rather than just taking individual points themselves. They clustered them first, and then they looked at the interaction between clusters. Okay, as a matter of fact. Then in the subsequent paper that Catherine Turner had suggested is we should be looking also like more of the global perspective of points that make up a persistence diagram. So they suggested a little bit of a variant of the original one, but both papers had basically a very fixed number, an initial fixed number of points on a persistence diagram. And that can be, in some applications may work just fine, but it could be very disadvantageous in other applications. So basically, what the last point says is, I'm going to consider a persistence diagram with 6 points on it. And I'm going to do my analysis based on that. Okay, as you can see, this one has already a restriction when it comes to data analysis. All right. So let's see how we did it. All right. So, and I'm going to talk about this noisy thing. This is the persistence diagram here. Okay. So what we do is we augment the original space. So the triangles here are these triangles that you see right here. Okay. But I augment the space, I augment the points in that space, in that domain, in the wedge, by various different points, okay? And then what I'm going to consider is I'm going to consider what I say here, Dirichlet tessellation. Think of it Voronoi tessellation, okay? So, and I'm going to assign weights which are proportional to the area. Okay, so as you can see here, I'm doing a little bit of a trick. The empty spot, the non-filled triangles are these augmented new P points, okay? And then somehow I stuff them on the bottom, okay? Why I stuff them on the bottom is because not necessarily all of them in the bottom, but what I have here, I'm kind of exaggerating in this image, to underline the fact that this region here comes with noise, it is associated with noise. Therefore, I really need to, when I sample new persistence diagrams based on this, I want to sample with low probability from the points along the x-axis, because these are the points that they are not interesting. They are just there due to noise. So I want to get persistence diagrams that they have very low probability. And how you do that? Because I do Voronoi, then I'm going to, and my weights are proportional to the area. I want to make the area as small as possible. Okay. And therefore I stuff them down here. So then these areas are very, very small. On the other hand, you can see that the prominent points are kind of like up there with higher probability to sample points out of these areas. And that will basically determine the spatial pattern. That will take care of the spatial pattern of the data. So that's the blue part in the equation. Now, the next part is the interaction. So this is an assumption that I have in my algorithm, or a philosophical assumption, if you like. We can argue as much as you like about this, but this is what we have done, is that nearby and distance point in a persistence diagram indicates similar and contrasting topological features respectively. And in that realm, we have this equation number 3, where these weights, theta, basically will tell you how strong or how not so strong the relationship between point I and point J is about. And that takes care of, for various R's, as you can see, okay? And that takes care of the interacting part of the process. Okay, something very, just to be a little bit upfront here, is that a lot of these models do have a lot of parameters, as you can imagine, the R's and so on and so forth. So you need to estimate them, okay? How do you estimate them? With a method that's called maximum likelihood estimation. But because it is hard to compute the normalizing constant, I use a pseudo likelihood approximation. This is something, if you are not familiar with that, don't worry about it. It's something very statistical that I have to say as an NDA. Okay, so now that I have a characterization of the spatial pattern, we are ready to basically draw samples and make inference about our problems. Okay, so what we're going to do, we're going to do this Metropolis Hastings MCMC, okay, where one proposes samples according to a proposal Q and then accepts them with a probability alpha. Okay, remember from the MCMC 101. Okay, now, unlike the previous studies, we are not going to have a fixed number of persistence diagrams. Okay, so I'm going to say that it doesn't really matter. Now, if it doesn't really matter, that means you cannot use just an MCMC, but you have to look into how the samples are going to be represented in the space. And to have that, your sampler has to have 3 moves. What are the 3 moves? Imagine that I am a point on a persistence diagram. So I will have a certain probability to move in my new generated sample. Okay. Imagine that in the underlying persistence diagram, you have in the original one, you are in blue region number 5, which is the noise. Okay. But I have this Voronoi with low probability. So that means when I sample, I will have the chance, I should have the chance to vanish with a certain probability, because it is the underlying noise basically that made this point appear there. So somehow I need to get rid of it. Or if I somehow, my persistence diagram did not have a topologically prominent point, figure it out, like really find it, then I need to give a chance to my sampler to somehow generate such a point. So a new point should be added to the persistence diagram. So my sampler is going to do all these 3 things at the same time. So move around points, get rid of points I don't like with a certain, all that in a probabilistic setting, or also appear new points that you didn't detect initially. Okay? So for that, you have to dig into something that is called reversible jump MCMC. And that's what this is all about. This is our brand new algorithm for the persistence diagrams that basically says, I start with this persistence diagram right here, okay? Then I'm gonna flip a coin with 3 faces. Okay, that's kind of weird, but think about it. You have a coin with 3 faces and has 3 probabilities: move, add, remove, PM, PA, PR. Okay, and then you're gonna decide, what are you gonna do? Are you gonna move the points? Are you gonna remove points, or are you gonna add points? Okay, so you pick with a certain probability what you do, and then you're gonna propose a new persistence diagram, D star. Okay, now if you have to, if the chosen is to relocate, and then you accept the sample, you see here that this guy has a new move. Instead of having DI, it has the DI star, okay, with a certain probability. If you add the point, then the new D star is going to have what you had before, the DL, plus the new point D star. And then if you decide to remove that point, you see that the new D star is going to be the previous one minus, you extract that D star, okay? And then you have to compute the probability of acceptance between the previous, the DL, and the D star. Basically, what is that acceptance probability? Remember, it is the penalty that I pay for sampling out of the proposal versus under the underlying, the true underlying distribution, the penalty you pay, okay? And then you repeat. Okay, so in case you were wondering, do these probabilities exist? Can I have a specific closed form solution, or is something ad hoc? The answer is this proposition. I'm not going to go through that, but the answer is yes, I can compute them. I can have them and evaluate them as they are given in the blue and the red form. For the relocation, if you move one point to the next, it's not difficult. It's just an MCMC. It's a vanilla type of approach. But for the move and the removal, sorry, for the addition and the removal, that's the formulation for these guys. Okay, so let's go now back to the next 5 minutes or so to the original problem that started all this. So we have the various grains, A, B, C, D, E. The idea is the A to D somehow should behave in somewhat similar relationship, a similar way, but the E should reflect something totally different. And this abides by the material scientists basically what they know, but haven't shown it when it comes to the Schmidt factors. Okay, so we're going to look at the Schmidt factors. And as I said, these guys are French material sciences. What they've done is they did a Kolmogorov set. So basically they say, okay, let me consider this histogram, this histogram, this histogram, so on and so forth. And I'm going to test the hypothesis. Is the histogram of type I, of temperature I, the same as temperature J for all IJ pairs, basically? Okay, for which the I and the J are the various different temperatures right here. Okay, so if you run that, so this is what they got. They couldn't differentiate anything. All the p-values are really large. Okay, so they couldn't differentiate. Okay, so all the materials behave in the Schmidt factors for these materials in the various different temperatures behave similarly. We don't see this, you know, the breaking point at 900 Celsius. Now, what we're going to do is we're going to do our approach, the persistence diagrams approach. but for the Smith factors. So now I'm gonna, how do I construct from functions, continuous functions, if you like, a persistence diagram? So you can use the sub-level self-filtration. Okay, so you start with a threshold here. Okay, you start with a threshold, and as you are increasing the radii, okay, you are increasing the threshold, and basically will give you the relationship, the modal the relationship between the peaks and the valleys in this function. That's what basically these points represent. So we do that for the histogram. How we do that with the histogram? We smooth out the histogram, and we do exactly this. So if you look at the Smith factor, for example, for one of these histograms, what temperature is that? 950. So then you get points like this. Okay. So these are the various different histograms in the persistence diagrams in the 5 different temperatures from 700 to 950. Red is 700, green 750, blue 800, 850 is purple, and 950 is are the brown diamonds. Okay, so we take into consideration these 5 different persistence diagrams, and we are going to apply on this original persistence diagram our algorithm to basically generate more persistence diagrams out of that. Because if I have only one, I cannot do a very good analysis, as you can imagine. It's a very biased analysis out of one sample. So, okay, so here is the idea. You use sub-level self-filtration to convert the Smith factor empirical distributions to persistence diagrams. For each annealing temperature, we generated a sample of 100,000 persistence diagrams out of that. So our analysis is going to have 100,001 persistence diagrams for each guy, and basically, now for the MCMC, instead of using basically for the MCMC, if you have these points here, we used something that we call a Gaussian mixture. So you could think like as weighted sums of some specific normals, okay, where each normal in somehow it is centered around the points with a variance that we learn, okay, that the variance we estimate. So that's what you could do for that. That will be your proposal density for your MCMC. Okay. And out of that, we got this, we generate these histograms of persistent values for each of the 100,000 persistence diagrams, and we run again that Kolmogorov-Smirnov test, and we report the p-values. Okay, and this is what happens. If you exclude the 800 Celsius difference between 700 and 800, the 700, remember, is that with a sparsity. Okay, if you exclude that, then we detect, as you can see here in bold, very small p-values. Okay, that means that the 950 Celsius does behave differently when you have this when you do this approach. Okay, that was kind of the success of this idea. Anyway, final remarks. So today I presented you with a random generator for persistence diagrams. So we view the persistence diagram as a Poisson interactive Hoyle process, okay, whose distribution captures both the global and the local features of the data. So the generator considers 3 scenarios, 3 cases: moving points, adding points, and deleting points. Okay, and basically this led to the reversible jump MCMC model, which, as we just saw minutes ago, we just applied it to this material science problem for detecting a relationship among different materials in different, the same material, different temperatures, different annealing temperatures. using the Smith factor, which is related to structure and strength. And with that, I'm all done.
Thank you very much. Are there questions? Yes.
Can you elaborate more on the process of once we've sampled the persistence diagrams, how you went back and found the?
I never went back.
Oh, no.
So you have these histograms, okay? Out of this histogram, I did the sub-level set, I got a persistence diagram. So you have 5 persistence diagrams. Based on this pattern here, okay, overlaid one on top of each other. Based on that, we generated 100,000 persistence diagrams based on that. And then we recorded the persistence values of these various 100,000 persistence diagrams, one for each family. Okay, so that means 500,000 persistence diagrams. So we created histograms out of these persistent values, and that's what we tested.
Okay.
You don't go back to the scene.
Okay.
Yes, please.
Hello, first of all, to introduce myself, I'm Vlad from Probability. So I'm someone new also to this seminar. I came specifically for this talk. Yeah, so one question that I have, in our models, of course, I'm from the probability side, and I was working lately in what we call long-range Ising model. This was long-range Ising model.
Yeah, I see.
So this was Ising, sorry. Yeah, this was in the context here, putting a bit in the context, the interactions between the spins were long range. So they were not bounded, like in your case, between RL-1 and RA, right? So I think my question right now is, I think that there you put a bound with these numbers, RL-1 and RL. And can you, and you get results with those bounds, but if you enlarge the spectrum of interactions, will this method crash at some point, or?
Well, everything crashes at some point, but I don't know. Look, we estimate these values, right?
Yes.
And these values doesn't say that the R's have to be a specific. Actually, all it needs, it has to be a positive number, as a matter of fact. So you can elongate the bound. So you can have a lower bound, don't know, a specific number, and the RL doesn't necessarily have to be super close. I'm not doing a discretization on the R value space. So I do, but that discretization doesn't have to be fine enough. It could be like longer and longer and longer, I suppose. It is not, again, this is not reflecting in our model here. Our R's are indeed closer into the, they are closer to each other. It is not fine enough. It's not 1/n, order of 1/n, but it's closer, perhaps. In the Ising model, this is something we can talk about it. How we perhaps it could be. I mean, it's an interesting thing that it's an interesting statement you're making. I don't know how it would work.
So to put it like this, we are in our models, we are still in the beginning also of the exploration. The nearest neighbor Ising is very well studied, also the criticality that is super complicated. Because I saw that you mentioned there also that there is a Gibbs measure types approach.
Yes, that's right.
And I got like, okay, there is a parameter in this Ising again that is beta, that is like 1/temperature, and then you have a critical.
Yeah.
And I was thinking like, does this mean something here? For example, if you have some criticality in this.
Yeah, I haven't looked into that, to be honest with you. I mean, it's a great point you are making.
Yes.
Yeah, it's interesting.
Yeah.
Awesome.
Further questions?
Yeah, I have a question about, so you mentioned on an earlier slide, taking your persistence diagram, taking not a Voronoi tessellation, but something similar enough, and using the areas there to.
Whoops.
Yes, there, okay. So, what I'm confused about is where these additional points P we're generating come in, because on the one hand, it seems like you're using this distribution or this area weighted distribution to generate persistence diagrams, right? But how are you generating these new points on this persistence diagram to inform that later?
Yeah, so this is that's a very good starting point, right? So the idea is, do you believe that the points let me start with this. If one believes that the points closer to the x-axis or the diagonal, if you like, are existent due to noise, that means you want to make the sampler to give you points with as low probability as possible. To do that, you stuff them into these points that you believe they are coming due to noise. Okay, and then you let the other areas basically, you don't have any unfilled triangles here, so you can have higher probability. So your generator will give you points around this neighborhood. That's one thing. It is, you can think of it as a Voronoi. Why it is a Dirichlet? It's because if you want to do it in a probabilistic Bayesian setting, you need to have some sort of prior information on how you generate this tessellation, and that comes from something that we call Dirichlet distributor. Okay, so that's the prior is a Dirichlet. So that's why. But think of it as Voronoi, that confuses you.
So you're kind of taking these points that we assume are noise, making them a little bit more dense so that we get a lot of small triangles.
That's right. Yes. Mm-hmm.
Was there like a heuristic, like how many of those points you put in there?
Yeah, I mean,
Or you just like try a bunch of different things and see what gives the best?
pretty much there is not a theory you have to do so many, right? The idea is not the number the important thing. The important thing is, if let's say, let me put it that way. If imagine I don't have the triangles, right? The unfilled triangles. So imagine I took the persistence diagram as is and used my generator. Whatever I have done, forget about this, I've done it here. Do you know what's going to happen? My generator is going to give me a lot of points around here because it's a high density, region. So my sampler will be getting confused and will be looking at this unless you do some important sampling and you try to highlight this like tail distribution basically. So you really need to do a lot of, again, tweaking and tuning and to the problem. So I wouldn't generalize very, very well to a certain extent. That's why I have to do this, to kind of like not have a high density region there. So that the sampler gets confused and draws samples from it. That's a great question. I mean, yeah, go ahead.
I have actually two questions.
Okay.
One is about the 100,000 persistence diagram. Just from the computational point of view, I mean, this is really massive.
Yes, it is massive.
And I remember in our Delta project and the REUs, well, we were, I mean, just a couple of them was partially even very hard. How did you do this? Did you have a supercomputer or what?
No. Everything runs with a small. I mean, you parallelize within your own laptop if you like, if you have a good laptop. But so everything runs on Python, so it runs very optimized on Python.
Yeah.
And but it takes a little bit of time, but it's not too bad actually.
It's not too bad.
Yeah, and we have this on. I should have mentioned that. I have it on my GitHub, so this can be downloaded and you guys can play around.
Okay, and about the degree, I mean, maybe I overheard it, but what is the degree of the persistence homology?
Oh, here is just a sub-level set, right?
Yeah.
So it is like 8.0. It's connectivity.
Oh, okay.
Yeah. So you push the threshold up, and you see how the valleys and the peaks, go about it. Yeah. So I'm not doing persistence diagram on the grains. You could do that too, if you like.
Yeah.
But that's very heavily. It's a heavy image. It's a really rich image. But we were interested on the Smith factors because that's what this guy's computing. So then you have a function, and then you have a histogram, an empirical distribution, which you can do the sub-level sets basically.
Okay.
To look at the modes of the distribution in some sense.
Yeah. And the last or second question was about, I mean, you started with this picture of the car and this.
Oh, yeah.
I mean, is that the work you have done, is that kind of ready to be applied in the industry or?
It is, because in the material sciences, this is through experiment that they did.
Yeah.
And I mean, this is a first approach that we were able to found this thing. Now, can I sell that to BMW? I don't know about that.
Yeah, okay.
I mean, maybe, sure. But I don't know how, you know, that's the material science job to sell the Smith
Yeah,
factors
okay.
to Motorworks or VW or Ferrari. I don't know.
Okay, any further questions? Then let's thank the speaker again.